Hello, lovely people. I hope you are doing well. Welcome to a video. It's a bit of a different one, but we're going to be exploring the Fibonacci sequence and its relation to this amazing special number. Let's get into it. So, first of all, what is the Fibonacci sequence? So, let's just write it out and I'll explain what's going on. So, 1, 2, 3, 5. So, to get every next term, I'm adding up the previous two terms. And to get my next term, it's going to be 5 plus 3, which is 8. Next term, 8 plus 5, which is 13. Next term, 13 plus 8, which is 21. Next term, 21 plus 13, which is 34. And the next term is 55. And the next term is 89, and so on. Okay, that's all well and dandy. What's going on here? What we're going to do is we're going to compare the ratios of each term. And what I mean by that is I'm going to take a term and divide it by the previous term. So if I take, for example, the third term here and divide it by the second term, so 2 divided by 1, that gives us 2. If I take the fourth term, which is 3, and divide it by 2, that gives us 1.5. If I take this 5 and divide it by 3, that's going to give me 1.6 recurring. If I take the 13 and divide it by 8, excuse me, I'm going to use a calculator because, yeah, 1.625. I feel like I should have gotten that. Okay. If I then take, let's go for a bigger one, so 55 divided by 34. Let's go on the calculator for this. That's 1.6176 roughly. 1.6176 dot dot dot. And then if I take 89 and divide it by 55, let's see, 89 divided by 55, that's 1.618 dot dot dot. So we can see that it's getting closer to some kind of number. And if we were to go to not the 100th term, not even the 1,000th term, not even the 10,000th term, not even the 100,000th term, or the millionth term, or the billionth term, or the trillionth term, or the quadrillionth term. But if I'm going even bigger than that, closer to the infinities, getting up towards there, and I had say an, but the term before that would be an minus 1, and the term before that would be an minus 2, and I've got like all my terms in between, and the term after that would be an plus 1. The ratios are getting so close that as you're approaching infinity, the ratio is essentially the same because it's approaching some sort of limit. So as n tends to infinity, the ratio of consecutive terms remains constant. So what can we do with that? Well, we can work out what this ratio actually is. We can work out the exact value of this ratio. And that's simply by saying that if we take an plus 1, which is, close to the infinities, that's just the term notation, divide that by the previous term, which we call an, well, we can say that's equal to an divided by an minus 1. Because they're so close, because they're all so close to infinity, we can essentially say that these ratios are the same. So this term, the n plus 1th term, if you like, divided by the nth term is going to be the same thing as the nth term divided by the n minus 1th term. Okay, and let's just call that limit L, because it's approaching some sort of limit. Okay, then we have, note that the Fibonacci sequence is also formed by taking the sum of the previous two terms. So this an plus 1 term over here is the sum of this term and this term. So I can replace a of n plus 1 with an plus an minus 1. And that's all divided by an. And that's supposed to be equal to an over an minus 1, which of course is equal to L as well. Now, I can simplify this. So dividing each term on the left-hand side by an, I have 1 plus an minus 1 over an. And that's equal to an over an minus 1. Now, if we look for a moment, first of all, remember that an over an minus 1 is equal to L. But what's this thing here? This thing, let me just point it out in a different color. This is looking surprisingly similar to this. That is just the reciprocal of this thing here. So if an over an minus 1 is equal to L, then an minus 1 over an is just 1 over L. So I can write it like this. And that's equal to an over an minus 1, which is equal to L. So I've set up an equation now in terms of that limit. And now this is actually a quadratic equation. We can solve this quite nicely. So I'm going to multiply everything through by L. So multiplying the 1 by L, I get L. Multiplying 1 over L by L, I get 1. Multiplying L by L, I get L squared. Quadratic, we make it equal to 0. So we've got L squared minus L minus 1, which equals 0. I'm going to solve this by completing the square because I like things complete. So let's go L minus half the coefficient of this, which is a half. Square that. Take away minus a half squared minus 1 equals 0. I've got L minus a half all squared. And that is equal to, well, not even equal to, take away minus a half squared, which is a quarter, take away 1, which equals 0. And then I have L minus a half squared minus a quarter minus 1 is minus 5 over 4, and that's equal to 0. And then I have L minus a half squared, which equals 5 over 4. And then square rooting both sides, I get L minus a half. I didn't really need the brackets anymore, but there we go. Equals plus or minus the square root of 5 over 2. Okay, now first of all, well, actually, let's work out what L is. So L is equal to 1 half plus or minus the square root of 5 over 2. But to tidy that up, that's 1 plus or minus the square root of 5 all divided by 2. Now, there are two answers. I mean, there's one that we're more interested in. So note how we were getting closer to this 1.6 value, which is positive. So we're going to use the positive square root because that's the thing that we're interested in for this particular sequence. So in actual fact, our L is 1 plus the square root of 5 over 2. What's the name of this? It's the golden ratio. Yes. Golden. So it's the golden ratio. It's used in so many things. So let's actually write down, we'll put this in our calculator, 1 plus the square root of 5 all divided by 2. And if you put that in your calculator, the calculator will spit out the decimal value would be 1.618033989, and the number goes on forevermore. It's an irrational number. So after all of our work, we were tending towards this kind of value. The ratio of the Fibonacci sequence actually approaches the golden ratio. It's pretty cool. Pretty cool. So thought that would be a bit of fun, something for you guys to grit your teeth into, and didn't really require too much additional knowledge. So let's have some fun with maths, guys. Take care.